series on decoding pandemic data. I'm glad to see we have a good crowd today on what I know is a day where our attention is divided. So hopefully this will take us away from one difficult thing to deal with and turn our attention to another. So anyway, I would say, Tom, thanks so much for agreeing to give a talk. So I would like to introduce everyone to Tom Trikalinos. Tom is the founding director of the Center for Evidence Synthesis in Health here at Brown University. And he also is leading the modeling efforts at the state of, or with the state of Rhode Island. Tom has really been on this from day one. And I think he was one of those folks who was working 26-hour days early in the epidemic, and maybe now his days have scaled back to 24-hour days. But Tom has really been instrumental in helping us understand what's happening in Rhode Island. And before he was involved in this, Tom is a person who works in the Department of Health Services Policy and Practice here at Brown. He has vast expertise in modeling, evidence synthesis, and in work in health policy evaluation. And he's also the recipient of a large number of NIH grants and grants from the AHRQ. And as I said, he's built the Center for Evidence Synthesis in Health here at Brown. So Tom, we're really pleased that you've taken time out, especially today where there's a lot of things going on. Really eager to hear about what you have to say. And with that, I'll turn the floor over to you.
Well, thanks, Joe, for the introduction and the opportunity to discuss some things. I understand the format is, in a sense, free-floating. What I will do is I will start saying some things and give you high-level observations and results as I go on. And, then when we get to the discussion, if need be, I can get into more details. So what I should like to discuss is about a type of modeling that is different than the modeling that people do for the whole US. So it's different than the discussion that Yvonne Ray did a couple of weeks back, because we are modeling only Rhode Island here. So we are going to use similar approaches, and I'm going to explain, but we are focused mainly on Rhode Island. For this reason, we have a very good understanding of what goes on in terms of how the numbers change daily. We have very good control over the quality of the data, and we actually have richer data than other teams have based on our collaboration with the Department of Health. And therefore, the predictions that we can make may be comparable or better than predictions that other teams can do, but it's not because we have some special sauce. It's because we have perhaps access to more clean data. So let me start saying this is reporting on work that is joined with colleagues at the School of Public Health and at the Policy Lab. So we have Jonah Pope and Sean Forbes at the School of Public Health, and John Fulton at the School of Public Health, Kevin Wilson, who is an excellent data scientist, works at the Policy Lab, and he's in charge of ensuring that all the data flows and all the automation goes smoothly. And then we have Maria Messick, who is a policy advisor for the governor, and Bill McQuaid from the government, and also colleagues of ours from other institutions, Nikos Trikakis in particular from MIT. So this is joint work that has evolved over quite a bit of time, and most of the mistakes, as they usually say, are the ones of the speaker, and so forth. So let me say things. This is something that everyone knows, that we had the epidemic going full speed in the spring, but then we had aggressive government measures and substantive change in people's behavior that have essentially curbed the epidemic, but they have done so at a large societal and economic cost. So the thing that is in everyone's mind is how to complete the relaxation of these measures. And we want to have a progressive relaxation of measures, but the more you relax the measures, the more you risk the pandemic. Now, I'm just going to give you some recent data to get us all on the same page. Rhode Island has approximately 1 million people. And if you exclude people who are in congregate care facilities, and here, when I say congregate care, I mean mainly nursing homes and long-term care, who are usually, the older and frail people, we are going to be roughly, 1,050,000. As of a few days back, we had a total number of positive tests almost in the 30,000. We have a large number of deaths, 1,200 deaths, but the majority of them are from people who are in congregate care settings. And I'm mentioning that, and I start splitting out the congregate care population because it was a major decision when it comes to modeling and how to deal with this population. And you will see later how we did it. Hospital census, meaning how many people we have currently in the hospital for COVID-19 related reasons. We have 170 and excluding congregate care, 150, and 22 people are in the ICU. So if I take a look at it's approximately 30,000 tests out of 1 million people. So the known cases are approximately 3%, but we estimate an attack rate more along the lines of 7.5% or whereabouts. So I'm going to just go through some plots so that we can see some of the evolution of the data. And this is a plot of the test positivity rates. In the beginning, we peaked essentially in the end of March, in the end of April, sorry, when it came to hospitalizations. The test positivity rate was very high in the beginning when we didn't have enough tests and we were testing only people who were coming with suggestive symptoms and signs of COVID-19. But then testing became more widespread and it came down. And once we entered the summer, we had enough tests to actually give to people who needed to be tested. We have a kind of an increase in the summer in the test positivity rate, and that increase may be related to a mini resurgence, let's say, that we had around the early July period, and then it drops down and then it picks back up again. And we know that we started testing the students in the beginning, end of August, beginning of September and in October, but this rise in the tests is not mainly because of the testing of the students. This rise in the testing results is mainly because we believe that we have a resurgence of the infections in Rhode Island. The cumulative cases identified, this is essentially the number of tests, the number of people with positive tests. You see that we are experiencing a rise now in the fall. Let me show you a couple about the cumulative deaths. These two plots, the red line is cumulative deaths in congregate care. These are absolute numbers, and these are cumulative deaths from people who are in the remaining population. So you see that the vast majority of deaths come from the congregate care. And it is not unexpected. It is expected because these are the frail people. But at the same time, the people who are in congregate care are in principle isolatable. They could be isolated from the remaining of the population. And I'm making this comment because I want to motivate the modeling choices that we did for congregate care versus not. In terms of hospitalizations, the number of hospitalizations grows at an, if you squint a bit, it's almost linear. So it's got more accelerations and decelerations, but it's almost growing linearly. And this means that essentially we are seeing this epidemic grows under the influence of the measures that have been taken in a more or less steady way. Most of the hospitalizations come from people who are not in congregate care, but a substantial proportion come from people who are in congregate care. This is the hospital census. This is the evolution of the hospital census, broken down into people who are from the community, Black, and from congregate care. And you see that these two lines, these are unsmoothed lines, just time series. They track each other very well, but they start diverging here. So we see that we have an increase in the number of people who are in the hospital currently since the beginning since the end, let's say, of September. The numbers go up. The dotted line is November 1, when the last day of these data was when the last day at which these data are available. But what you see here is that we have a difference in the number of people who are hospitalized from congregate care. So this might mean that we have successful measures in place so that the way that the infection does not pick up in nursing homes and in long-term care facilities, at least in the same rate as it picks up in the population. So these things, these observations that we see, that a large number of the deaths come from congregate care, a substantial number of the hospitalizations comes from congregate care, was the motivation for a decision to actually split out the modeling into two parts, to model people who are in the community separately, in a separate way than how we model people in congregate care. Congregate care is the CC. So I'm going to give you an idea about what the modeling in the community looks like, and then I'm going to show you some results and stop there for discussion. But the general thinking is as follows. People who are in the community, we are going to model them using a compartmental epidemiological model, actually using ensembles of compartmental epidemiological models. And I'm going to describe some of these ensembles, some of these models later. And the idea for these models is that you can think about them as nonlinear regressions, where the functional form is known, is actually highly prescribed based on the structure of those compartmental models. And what they try to do is they try to fit the data, and the data are various time series and survey results. So for example, we have daily numbers of cumulative dead, of cumulative dead people who died in the community or died in hospital. The cumulative number of people who get discharged alive from the hospital, the cumulative number of identified cases, this is the number of positive tests, the number of tests that are given, and the number of positive test results among the tests that are given every day, and how many people are in the hospital, in the various wards, medical, surgical wards, and in ICU. So these are the time series, these are the data that our multivariate regression, nonlinear regression is trying to fit. And it does it for the community transmission model. The idea is that people in the community, more or less, you could, if you squint a bit or a lot, you could assume that they would be mixing relatively randomly between them. But the people who are in congregate care are kind of shielded from the community population. And the way that the congregate care population acquires infections is through visitors to the nursing homes, for example, or the staff, either healthcare providers or custodial staff who come from the general population to the nursing home to work. And therefore, once an infection gets in a nursing home, we expect that it would spread quite fast and it would have a big impact, but it does not necessarily result in new infections in the community. So essentially, the way that we model cases is that we have a compartmental model that describes infections in the community, and then we have a series of statistical models. These are time series models that are trying to predict the daily number of cumulative deaths from congregate care.
Wow, that's cool.
From the new cases from congregate care, the hospital census of people in congregate care, and the ICU census, and so on. And they do that by using lagged variables for these, and also in using information about how the numbers for these time series look in the community, and therefore those two models go on in tandem. So when we do our modeling analysis, we have, I'm going to tell you, a Bayesian computation algorithm that handles the transmission in the community and jointly estimates the statistical models for the congregate care, and is therefore able to give predictions for the total number of cases and so on, but it handles those two pieces completely differently. I'm going to show you some inputs that we give for decision makers, but the decision-making problem, if I may simplify it, is the following. We have to choose between three things. Should we move ahead and further relax measures? Should we continue at the status that we have now, whatever measures we have, or should we retighten measures and move back? And this is the decision-making that we are going to try to inform. The general idea is that we use the models to infer the status of the epidemic. Then we do a projection in the future, and we examine some triggers that have been elicited based on the decision makers' attitudes towards risk and ambiguity. And if those triggers are crossed, those thresholds are crossed in the model's predictions, then we essentially sound an alarm. And you will see what this looks like later. So in some abstraction, for those of you who are used to feedback systems and control, we have a system, which is the epidemic. We have a monitor of that system, which are our triggers that we are monitoring and predicting based on the modeling. And then we perhaps give feedback where we adjust measures and the loop continues. That's not a critical slide, so I'm not going to focus here. I started saying that we have models and ensembles of models and model variants, and I'm going to say a few words here before I start describing the mechanics of the models. And I want to actually speed up quite a bit. So when you model, let's say, a hurricane, you model the weather, you are modeling nature, and no matter what the outcome of the modeling is, the hurricane is going to come or not going to come. But when you're modeling a system that has reflexivity, a system that can react to the predictions, like a societal phenomenon or a man-made system, then the system will react to the prediction, and therefore the forecast will affect the future. And the whole epidemic is governed by human behavior. The force of the epidemic is governed by human behavior, and all our predictions, therefore, cannot possibly be very far ahead into the future. Because even if we, for example, predict a catastrophe, we would hope that the decision makers would react, and therefore we would avert the catastrophe. So I'm going to be showing you look-aheads that are roughly a month or 2 months in the future, and no longer than that. In fact, the CDC actually does look ahead only for a month in the future, 3 to 4 weeks in the future. So we have various models that try to predict the future based on different degrees of similarity with the past, and the various models differ with respect to this similarity with the past. And because we have many such models and they give somewhat different predictions, we are creating ensembles of several of these models variants, and these ensembles can actually give aggregated predictions. So let me give a very high-level description of what I meant when I said that we have that we are fitting a regression on a compartmental model. So you have seen these models before. This is a very simple representation. It's not the actual model that we are using, but it's an earlier version. But it's simple enough to describe. The population is partitioned into these 5 compartments: people who are susceptible, there are people who are exposed, but not yet infectious. There are people who are early in the infection that do not have symptoms. They do not have symptoms, but they can infect others. Then there are people who may develop symptoms. Not everyone will develop symptoms, and in the end, people are removed. So you can see that as a sequence of stages. And what drives this is an infection process, and the infection process happens here. People who are in the infectious states, meaning people who are early infective or infective in various categories, will come together with people who are susceptible, and they will infect some of the susceptible people. So there's this interaction between people who have infectious potential and people who do not have the infection yet is what drives the model. So this is a typical SEIR model or some expansion of an SIR model. The idea is that we are trying to fit the parameters that govern this model using a Bayesian computational algorithm to various data that are available to us daily. The data that I told you before, and also results from a relatively random seroprevalence survey that happened mid-May in 2020. Excuse me. And depending on the flavor of the model, this computational algorithm, the Bayesian computational algorithm, actually can be taking its sweet time. So some models are fit within 3 hours, some models want 20 hours to get fit of computation time. And this is our daily routine. Let me try to give some intuition in this simpler model about how what we are trying to do. What we're trying to do is the following. If the infection were unmitigated, then very fast all the susceptible will go through the infectious process, and they will either die or get immunity. But that would result in an exponential growth, and then in the beginning, and then a tapering off, and then a reduction in the number of the susceptibles to whatever the final number would be for herd immunity. But what we see is that we are not in an unmitigated scenario. So there's something that puts a brake on the epidemic, and the brake on the epidemic is being put by the measures that we take, that the government takes, and the behavior that we as persons adopt. And therefore, what we have to do is we are fitting a Bayesian computational algorithm that tries to estimate every day how much of the brake is being applied on the epidemic. So if the epidemic was completely unmitigated, things would have been over by now. But we grow at a more or less, steady state, a bit superlinear, a bit below linear, depending on the period. And therefore, it means that whatever we do as a community puts the brakes on the epidemic compared to what we would see otherwise. And all the game is how to estimate this braking function, and I'm calling it the dampening function. Very quickly, I'm going to give you an idea. In this simple system that I have drawn here, the dynamics the rate of change in the susceptibles is governed by how many people you have in the susceptibles compartment, how many people you have in the infectious compartments, a function of these, because there's contact tracing and quarantining and other efforts, but a function of how many people are infectious. The infectious will come together with the susceptible, and they will increase the rate by which the susceptibles get depleted. And this constant, this factor here, not a constant, this factor alpha of t is essentially the factor that encodes the breaking of the epidemic. And we are actually modeling it in the following sense. We say that if the epidemic was unmitigated, this alpha of t would be an alpha naught. And this alpha naught is related to the full force of the epidemic. But as time goes on, we have a dampening function that puts the brakes on the epidemic. So this is the effectiveness. The B of t is this dampening function, is the effectiveness of all the measures that we take. And 1 minus B of t is whatever remains of this alpha naught factor to propagate the epidemic. So the goal of the computational algorithm is to see the data and actually try to find what this B of t function should look like so that we see the stuff that we see in the evolution of the numbers. There are other caveats that I would make, that we assume this to be a closed system. We have no demography, births and deaths apart from deaths from COVID, but I don't think that this is a big problem, and I will explain why later. That's an example of an inferred B of t function from the model. What you see here is a point estimate, a 50% confidence band and a 97% confidence band. And what it shows is that essentially, there had to be breaks that in the epidemic from a completely unmitigated beginning, so that the numbers can come down, and then since the period of in May, when we dropped the epidemic down, our effectiveness has been relaxed, and actually we have gotten out of lockdown and so on. When the lockdown got instituted, we got into a great dampening, and then the dampening has decreased. So I told you that the model that we use is a bit more complex than the previous one, but it's kind of like the same idea. You have susceptibles who get exposed, who are pre-symptomatic, and then get into various stages of infectiousness. And there are people who are infectious and they're known and live in the community. Some of them will recover and some of them will die. There are people who are unrecognized because they have not been tested, who live in the community, and they will be remaining unknown, and some of them will recover and some of them will die. And then there are people who get into the hospital system, and some of them will get into the hospital, some of them will get into the ICU, some will die while not being in the ICU, some will die in the ICU, and so on. And therefore, what you have is a system that has a lot of transition rates. The stuff that I'm showing you here is just how this model is organized. Red stuff are things that are observed, that are assumed or obtained from the literature. Blue quantities are things that are obtained directly from data by analyzing our data from hospitalizations and so on. So for example, this T is the average time that it takes from people to move from this infectives one compartment to the child compartments or the next compartments, and we obtain it from the literature or from assumptions or from fitting it through calibration. I'm not going to stay too much here. These are helper graphs that I have created that essentially tell us how the various probabilities relate to our data and to assumptions from the literature. And just to explain something is that the proportion of people who are in this DH compartment, so this is the discharged dead from the hospital. This is this compartment, discharged dead from the hospital. The proportion of people who are in this compartment will be determined by how many people we actually see in the time series and how many people we have in the population, in the whole system. So it's going to be modeled at every time, conditional on knowing this parameter is going to be a binomial distribution, or actually this whole thing is a multinomial distribution, and so on. So the data, the observed counts, correspond to proportions for some of these states, the blue states, or for summations of some of these states. So this whole system and the stuff that are in blue background are time varying parameters. So this whole system, I'm gonna go over these. This whole system is being modeled, and essentially we have different models that differ in how we apply the breaks, in how we specify this B of t function. And we have tried several things to do this B of t function, but in general, the modeling of the B of t function has a temporal component, something that changes over time, and optionally it has covariates, which are optionally subject to regularization penalties. I'm going to just tell you that we have tried seen as covariates the government measures and the Google mobility data for Rhode Island, using or not using lasso penalties. In the end, we haven't found that the covariates are useful for our type of modeling. And in general, they also lag many days back, so they're very problematic. So in the end, we are focusing attention to various functional forms for this B of t function that are either splines or autoregressive models, and we have moved recently to various autoregressive models. Let me quickly comment on triggers for decisions. I did say that we use the models, we get predictions in the future, and then we decide whether we should be given an advice, quote unquote, to move back in terms of measures, regress to stricter measures, that we could further relax measures in the next month, perhaps, or keep current measures. So these are some examples that, for example, we would move ahead if we are 50% certain that the number of ICU beds that we will need in the next 60 days is going to be less than 133, and we would be moving back if it's above 162. So what is this 133 and 162? These are numbers that we obtain from the hospital systems about the capacity that we currently have. And the total number of beds, similar numbers, new hospitalization, similar numbers, and so on. So these are indicative numbers. We have actually several scenarios of triggers, but these are the ones that I'm going to show you. So the idea is, for example, that if I get the density of the people who are projected to be in the ICU at a particular day, at a particular point in time, that density would have a mass above this top threshold, a mass below the lower threshold, and the remaining of the mass in the middle. So I have these three probabilities that sum up to 1. And if this probability P1 is above 80% of the mass, we are going to say we should regress to stricter measures and so on. So in order to visualize this over time, first observe that these three proportions, because they sum up to 1, they essentially live on a triangle, or on a simplex, on a two-dimensional simplex that is this triangle on the three-dimensional space. So for example, if the probability P1 is 1, the other two probabilities have to be 0. So you would be in this corner of the triangle and so on. So at any point, the modeling gives us a vector of these three probabilities that can be plotted on this triangle. And if we imagine that we look at this triangle and this simplex this way that the arrow shows, and we do a change of bases, then we would be looking at the triangle like I show it here. And essentially what we see is the vector of these probabilities. And I'm going to be showing you plots that look like this. So this is an example of these trigger plots. And these are actually trigger plots for one of the models that are very recent. What does it say? It says that currently we're in the black dot for all three. Let me go here. Currently we start here, and the prediction of the model is that we should be living in this green area, and that green area corresponds to the cutoffs that are suggestive that we could go ahead. But within 60 days, you see that we are moving into the yellow area, which is this thing that says that you should not go ahead and you should stay where you are with respect to the total capacity of beds. This is with respect to the number of new hospitalizations every day, but we don't think that we should be seeing an overrun of the number of the ICU beds. So some results with three model variants. I was hoping to actually have completed the full ensemble estimation, but we are still in computation for that. So what I'm showing you is some results from things that have finished computation, and these are three indicative models that can give you a sense about how the predictions evolve with each one of these three models from August 1st till today, and looking ahead into the future. So these three models, I'm going to name them model A, B, and C. They are autoregressive models of moving averages, and they're using a particular time varying offset. It's a technique that I'm not going to describe. But we have three models. Model A is one that tends to show less aggressive growth, B, a bit more aggressive growth, and C, quite aggressive growth in the number of cases. And actually, it would help me to just move back and forth a bit. So I think that you can see this slide well enough. These are the number of people who are predicted to be in the hospital census, including congregate care. The model predictions are the blue thing, the blue ribbon, and the real numbers are the red line. The dotted line here corresponds to mid-August, and this is where all the information from the model has been censored. So the model is using data up to 8/15 and does the look ahead, and then we see how things realize by looking at the red line moving ahead. So in terms of the hospital census, you see that this model kind of misses a bit. It's not in the band, but it's also not qualitatively far away. I should say that comparing this type of performance with the performance of the models that do hospitalizations in the CDC website, this type of performance is much, much, much better. So, there's several models showing order of magnitude differences at the CDC website. So this is the least aggressive model. You see that the least aggressive model, it was working pretty well in the summer, but since the start of the fall, we have a rise in cases. So if I go here, you see that there is a rise in cases, and the model does not pick up the rise in cases. It gets into the blue area, but it doesn't pick it up. So you will see that 9/15 it starts picking up. If we censor it at 9/15, it starts picking up the rise better, and so on. And this model is generally speaking is got a decent performance. A more aggressive model is shown here. This more aggressive model, model B, would not be favored in the ensemble if we were using it back in August, because it would be quite aggressive. It would be overshooting, but it actually does pretty well in the fall, in the sense of following the number of hospitalizations picking up the trend in the fall. And the trajectories and the way that the ensemble works, we have results from an older ensemble that we created in the summer, but this is a new model that we have created in the fall, and therefore we need to recalculate the ensemble. The ensemble is calculated using an adaptive algorithm that essentially looks at the performance of the models in the recent past and favors the ones that gives bigger weight to the ones that have better performance in the recent past. And therefore, we would expect the ensemble to actually do what it did in the past, meaning to favor the least aggressive model when there's least aggressive growth in the recent data, and start shifting to the more aggressive model when there's more aggressive growth in the data. That being said, I'm going to just show you some key trajectories that we have here. So, for example, the number of people who are dead, known dead people, known dead people in the population. This prediction goes out to 2 months, 60 days. I remind you that the CDC models do a prediction that stops at 1 month, and you can see that the prediction that these models have is at least decent. In fact, they're very competitive with the best models for Rhode Island that the CDC has, and with the CDC ensemble. So what I'd say is perhaps I spoke more than I planned to, so I'm not going to get into the optimization stuff, and I'm going to stop here, Joe, and actually, let people make comments or ask questions.
Okay, Tom. I mean, this is the sweep of this work still, you and I talk every other week or so, and the sweep of this work still amazes me every time I see it. It's really fairly amazing. Let me open the floor here. I sent a note out to the crowd that you can either submit questions or raise your hand. It looks like we have one person. Chris, you just have to unmute yourself, maybe just say who you are for the benefit of everyone else, and then go ahead with your question.
Yeah, hi, this is Chris Schmidt. I'm chair of Biostat and also Tom's colleague at Evidence Synthesis and Health. Tom, amazing work, great talk. I had a question. When some of the raw data you showed earlier, they were quite, I don't know what's the technical term, but the time series seemed to be quite jumpy. And I was kind of wondering whether that was due to the fact that some things are reported more on weekdays than weekends or something like that. And how does that affect your modeling when you don't have like a smooth, do you smooth first, or how do you deal with that? Thanks.
So indeed, and actually, if let me start sharing again. There is a day of the week effect. For example, these spikes. Let me go here to the hospital census. So these ups and downs. And the ups and downs in the tests, this is what you referred to, Chris, isn't it?
Yeah, that's what I meant.
So there is a day of the week effect, and you can see that things every weekend, during the weekend, we don't have the same numbers reported, but on Monday we get augmented numbers, and then they get summed up on Monday. So indeed, there's an effect like this. There is no extra smoothing that we do to this time series before getting into the model. All the smoothing essentially happens through the model itself. So if you think about it, the way that the model works is that it says, I'm going to take this, any number that I have here on any particular day, or any vector of numbers, and I'm going to say that they come from conditional on knowing the parameters of that multinomial. They come from a multinomial distribution. Now, this multinomial distribution, the parameters of it are essentially obtained by solving the differential equations that govern the epidemic, and they have baked into them that B of t function, that dampening function. So the smoothing happens essentially from the model itself. It might be actually advantageous to do this and perhaps remove the weak effect or the weekend effect before actually feeding things into the model. But believe it or not, we didn't have time to even do this.
Yeah, I mean, I've noticed recently looking at the data that while Rhode Island doesn't usually report on the weekends, I've noticed that recently they've been reallocating the data to, whatever, I guess Monday they report for Saturday, Sunday, and Monday, so they reallocate it. So to some extent, you do have the complete data, but they're just not reported at the same time.
True. And this is another thing, that the data change day by day. For example, today's data tomorrow would be somewhat reallocated. So there's
Right.
some volatility and imperfection in the counts that you have, but we don't do any special correction for that either. So it's kind of smoothed out by the model itself.
Right.
So Joe, when I picked November 4, it was rather than October, it was because I was really hopeful that we would have the ensembles. So that I can show you actually both the algorithm that does the ensembles and the ensembles themselves. But we got delayed in part because we actually do an analysis on vaccinations and vaccination strategies and vaccination allocation. It's not that the state has a lot of leeway, but we have some suspicion that there are things that should be explored. So I did not talk to you about the vaccination part of the modeling, but essentially it has two flavors. One flavor is using this more complex compartmental model with extra states and some tricks to ensure that people don't get doubly vaccinated and so on. And it's essentially a propagation of the MCMC final state in the future. Because vaccination has not started yet. And there's another version that uses an agent-based model that is a different approach. So we have a couple of alternative things that we are doing for exploring vaccinations, and the goal would be, for example, to find quote unquote optimal or near optimal vaccination strategies. It's a difficult problem because it's a control problem of a dynamic system, and we really plan on solving it just by simulation. So we're not going to do anything fancy in terms of the optimization math of it.
I think having a really accurate representation of the epidemic dynamics themselves, I think is going to help get that optimization probably closer to what you'd like to see. Like what would be the true optimum, I guess.
Right. And this is where the need is for the agent-based model rather than the big compartmental models.
Let me pause here to see if anybody else wants. I've jotted down a couple of questions, but I want to open up to the audience to see if others have
Sure.
questions for Tom. Tom, let me ask a meta kind of question. We've seen, those of us who just consume the daily news see all these different models, and then you can look at the Rhode Island model. And what really strikes me about the work that you and your team have done is that it really amplifies the importance of localized models rather than, I think that just on my reading of some of the state-specific models, they're often, if for those of us who look at hierarchical models, like a model of the nation, and then there's like shrinkage estimates for each state, and that sort of thing, when you have such severe asymmetry across states, doesn't necessarily work very well. Do you have anything that you could share about like how decision making is made at the state level when it comes to weighing sort of the localized evidence like you're generating versus national evidence? Is all that come into play? What's the process? Because it sounds like you've explicitly designed this for decision making, which strikes me as really like that's like right on target for the sort of thing a localized model should be doing. But how does that play out?
So a couple of comments. So with respect to the local tailored modeling versus the more global one, I'm part of the MIT Delphi model, and of that group that creates the MIT Delphi model, and that model is a global model. So it does not only the US, but it does generally the whole world. And I mean, it's a simple model, right? I mean, it's just essentially 3 compartments with some splits, and it has only 7 parameters that are fit with an algorithm that is some trust regions algorithm that fits those parameters, and it's just not adapting well to the data locally, but it does give a very good idea, if you will, about what happens in a more abstract scale. So we don't, for example, we don't use the predictions of the MIT model, not because I don't like it. I mean, I like it very much. It's just that we have created a much more tailored version, and I think that the tailored version pays off. Because you can actually leverage maximally the information that you have. Now, with respect to how these models are used in decision making, I'm not going to say how they are actually used. I'm going to say what the process is and my impression about how they're actually used, because I haven't spoken with the governor. What we do is we work with the governor's policy advisor, and we are lucky that she is an MIT graduate. She knows DFQs, so you can speak with her maths, and she can understand things without having to explain and say things in lay language. So we have sped up our development cycle. So we meet regularly, and we give regularly updates from this model and also from other models that we maintain. So we have a qualitative discussion with her, and she is the point person who is actually disseminating the translated information to the governor and to other decision makers. So we think and we believe that these models are being used. We have not been showing results to the public, not even to our colleagues at Brown. And I don't know what part of this the governor actually shares, but we know that the governor sees those models. I mean, we know that she sees our output, and we believe that it is informing their decision making. But as I said, I haven't spoken with the governor, and I think that I would have to speak only if things go very, very south, and therefore I'm glad that I don't have to.
Well, I think the person you're referring to is, I don't think she would mind us saying, is Maria Messick. And she's really, really extraordinary person, and like you said, she's really well versed in technical things, and seems to be able to speak our language and then the language of others who don't understand.
There's another comment that I would like to make, is that right now it's October. We're many months in this business, and we have a set of models that we can run regularly. Kevin Wilson from the Policy Lab has helped us productionize them in the sense that handle the day-to-day reporting that goes to the governor's dashboard, etc. But in the beginning, we were still developing those models, right? So all through the first month, for example, I could not have any output. So we were relying heavily on variants of deterministic models that look like that were just, based in built in Excel and in Mathematica. And these were different implementations of the same ideas done in different systems so that we could have some basic quality control. And until today, we actually have our colleague John Fulton, who is a very experienced infectious disease person. He's not an infectious disease doc. He's a cancer epidemiologist, but he's got experience through handling infectious disease outbreaks for Rhode Island. He still maintains daily a deterministic model, and we cross-check our model results. And we have trusted colleagues elsewhere. Massey H. Bonney in the University of Pennsylvania is another person who regularly sends us results of his model, and it's then not only an ensemble that we are trying to create of these Bayesian models, but also a bigger ensemble of the deterministic models and some select models from trusted colleagues. And all of these things are tools to inform decision making. They're not dictating decision making. They're tools to inform decision making.
Yeah, that's actually a really helpful answer. And I think this notion of ensembles is, again, it's something that came up during Evan's talk. It seems like this is the sort of the MO in what you say, like instead of dictating decisions, informing decisions seems to be the right approach. It's just really striking, like how accurate the models have become over time. It's encouraging, I think.
I mean, but at Christmas, during Christmas, these models will not probably capture the spike if one exists, and the same thing for Thanksgiving. So they still have to be modified to actually account for known family events, right, or known gathering events. So they would have to be adjusted, and this is why the dynamic mixing of models that have recent good performance is quite important, because you would see a switch from models like Model A to models like Model B between the summer and the fall.
Mm-hmm.
Right. Here we have to make decisions with great uncertainties that are beyond the uncertainty that we are willing to quantify with probability distributions. And I have spoken to you about this before, but in general, we can conceptualize uncertainty as aleatory uncertainty, or uncertainty that we can describe with our sampling distributions, and non-aleatory uncertainty, or Knightian uncertainty, or ambiguity. So things that have to do with the structure of the model. So we are trying to be robust over models. And one way to do it is to do it by an ensemble that gets an average of the models. Other ways to do it is to actually specify and solve a robust optimization problem that would say, can I find the models, can I find strategies, or can I find predictions across a set of models that would be robust against some worst case scenario and phenomenon. And this is a thing that requires quite a bit of computational power, and we have not implemented yet. I hope we will before this is a moot point, but.
Right. Okay, I'm seeing we're at the top of the hour.
Yep.
And I want to respect your time and everyone else's, and just express, my gratitude as a colleague and as a Rhode Island resident for all this work. It's really remarkable, and I'm also equally glad that it's being done out of the School of Public Health. I think that's.
You are exceedingly gracious as always, and let's say my wife says I talk too much, so.
No, this is all very good information, and thanks again. So I'll get to see you, of course, but I think we'll also have the work posted. So
okay.
if that's okay with you, we'll check with you about the legal stuff.
No, yeah, you can post. I don't think that I revealed any secrets.
Okay, All right. Well, thanks so much again, Tom, and we'll see you soon.
Thank you. Be well.